It picks up everything.
Okay, we will now dive into the world of causal sets with Sumati Surya, who will tell us about causality and the quantum gravity path integral.
Thank you, and thanks to the organizers for inviting me to this very interactive, very interesting conference. I've learned a lot from the talks, as well as the discussions and one-on-one interactions with people, so I've really enjoyed it. Thank you very much. So this is picking up too much. Okay. Yeah, it's okay. It's fine. Okay. Last week you heard a little bit about causal set theory. Faye Dowker gave a talk. So this will be a repetition somewhat, but also some of you were not there last week, so I will use it as an opportunity to give you some flavor of the motivation behind the causal set approach to quantum gravity. Where do I? I can just see now if it works. Yeah. Okay. Yeah. So here's the outline. I'll begin with the motivation and motivation for causal set theory based on just Lorentzian geometry. Then I'll discuss something about the dynamics, quantum dynamics of causal sets. Starting with, this is a review talk, so there'll be stuff that's been done over the last decade or so on the Lorentzian state sum models. Some numerical experiments that we've run, where we're at, and more recent work on the Lorentzian path sum, which is basically the full quantum partition function. And I'll end with just a little advertisement about a couple of new developments by people in the broader community. And I'll end with finally with conclusions and open questions. And these are the various people that some of this work has been done with. So let's just go to the very beginning and ask why causal set theory at all. If I think of Lorentzian geometry, and if that's the spacetime that's what we think spacetime is, a Lorentzian geometry, in other words, one with a signature minus, plus, 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 etc., in any dimension, then this very obvious thing that emerges from this is something called a partially ordered set. And this was, in fact, noticed very way back when, right after special relativity, by this person called Rob, I think A. Rob, and where the order structure of Minkowski spacetime became, he sort of said, here's a very fundamental property of Minkowski spacetime, which is the ordering of the events on the spacetime. And so if I think of causal order, which is, the standard definition on a spacetime, so consider your, with the required amount of differentiability, etc., then you know that there is a causal ordering on events based on whether there is a causal curve that connects them. In other words, a curve whose tangent everywhere is causal, so either null or time-like. And this, if you, in addition, require a principle of causality, so you say, I want to only consider spacetimes which are causal, then this relationship is acyclic, which means that you can't go back, you don't have closed time-like curves, and that's a property of this order relation. But it's also transitive. I think I forgot to write that there, but here you have it, transitivity, which is that if X precedes Z and Z precedes Y, then X precedes Z. Okay, so there's a transitivity. This simple structure of the causal relations, acyclicity and transitivity, implies that what's underlying a causal Lorentzian spacetime in any dimension is a partially ordered set. Okay? That's the mathematical structure associated with a Lorentzian spacetime. And it's very specifically associated with this signature. We know it can't be there in Riemannian spaces. There are no light cones. But also in spaces with two time directions, There is no way that you can distinguish a future from a past because the two time directions are connected. And here's an example of that, one dimension lower. But and that's actually very important. The structure of light cones, which we take for granted, this disconnected structure of future and past, is essential to this very important mathematical structure, which is that this object is a partially ordered set. And when I say there's a partially ordered set, even though it's coming from the spacetime, I'm thinking of M as simply the set of points on the manifold. No differentiable structure, nothing, and an ordering between the elements in that set, okay, between the events in that set. That is a mathematical structure. So, and this is a quote from Penrose and Kronheimer's 1960s paper, I guess 1967 paper, where they think of causal structure as an essence of Lorentzian geometry. And this is a question people have been asking for a while, which is how much information does this set contain? So is it some derived structure which has some skeletal information about the spacetime, or is it rather important? How much information does it contain? And last week, Faye also pointed out to this theorem, which basically says that it really contains a lot of information. And I'm just going to go over these couple of things, which is the idea of a causal bijection. So if I have two spacetimes which have their own causal structures, and I can map as a bijection, map one causal structure to another. Okay, that's a causal bijection in both ways. And then I'll consider conformal isometries. And it turns out that, and so let me go to the second theorem. If a chronological bijection, which also happens to be causal, between two spacetimes, and future and past distinguishing is a particular causality condition, which is very, very general. So if such a bijection exists, then those two spacetimes are in fact conformally isometric. So in other words, there's a huge amount of information up to conformal factor. All the information about the spacetime is there in this mathematical structure, which is the causal structure poset. The only thing missing is the volume element, the local volume element, which is basically the conformal information. So that structure is very, very rich. Earlier, there was this work by Zeman, Alexandrov, and Ovenichkova, which is in Russian, but then the same result appeared many years later, that even in Minkowski spacetime, if you look at the group of causal automorphisms, so you map Minkowski spacetime into itself, then that group of causal automorphism basically is the Lorentz group up to dilatations. So there's a really huge amount of information in this. It just doesn't have the structure that we're used to thinking about in terms of Riemannian spaces, or quote-unquote pseudo-Riemannian. And it's very much linked to the fact that the structure that we have is a Lorentzian spacetime. It's absent anywhere else. So here we go. We say, all right, let's take this seriously. And again, this is a sort of echoed in the literature from since Penrose and Kronheimer, and by many people later, that maybe the right thing to look at, rather than think of spacetime as a pseudo-Riemannian metric, but think of it as essentially a different mathematical structure, which we want to then quantize, not as a metrical structure, but in order theoretic terms. So this is the idea that that's behind causal set theory. We take this very powerful theorem due to various people, HK, MMKP. So there's a Hawking and there's a Penrose, and there are many other people in between. And this theorem basically allows us to separate the causal structure and the volume. And that already we know to be acyclic, transitive, it's a poset. But now we add in a condition of local finiteness, we discretize it. So if I have the continuum, and here's what I call an Alexandrov interval, which is a causal diamond, more popularly known as a causal diamond, which is the intersection of the future of this element at the bottom and the past of that element on the top. And I try to discretize it with respect to the causal structure. I have something like this. And I would like this volume element to be recovered by associating with every finite volume region a number, okay? A cardinality. So cardinality replaces volume, and this is what I do here. And then, of course, I want to, just like the tablecloth trick, I want to snatch away the space-time, and what's remaining is only the structure here. And that's supposed to be the fundamental structure of Lorentzian space-time. And that's the that's the hypothesis. And by causal set, we mean a locally finite poset. So let me quickly define local finiteness. It's basically capturing this idea that finite volumes have a finite number of elements, but technically you can write it as the fact that any element x and y, that the intersection of their futures and pasts has only a finite cardinality. So I'm going to give you a quick experimental demonstration of my favorite experimental demonstration of a causal interval. Again, if that was 1 second, it contained about 10 to the 170 Planck volumes. And in that is basically the number of fundamental elements of spacetime that it has. Okay, so that's the scale that we're talking about, but those are the covariant objects that one is trying to quantize. So here's the causal set hypothesis. The causal sets, or these locally finite partially ordered sets, are the fine-grained structure of space-time. And these are the people behind this idea. And if I left it at that, and I just said, well, let's just look at post-set theory and just try to quantize post-sets, that would give me theories which have nothing to do with the continuum from which I was inspired. And there are approaches to, which use post-set theory, approaches to quantum gravity, and I want to distinguish causal set theory from them, because one very important thing is the fact that we want to ground the theory in this theorem, which tells you that order should correspond to the causal order in the space-time, and the number of elements should correspond to the space-time volume. In other words, we need a very clear prescription for a continuum approximation of the underlying causal sets. So I use the word approximation because a continuum is supposed to be emergent in a very specific sense, that the underlying reality of a fluid is really molecular. Okay, so it's very similar to that. You can assume the continuum for many important technical purposes. It's easy to calculate things, easier to calculate in certain cases, but underlying the continuum is this discrete substructure. Yeah.
The previous slide, continuum, discreteness, and discrete. I don't quite understand exactly the difference between the last two. So,
I'm using the continuum to define this discretization, because I want to be able to make a connection to that Lorentzian theorem on Lorentzian geometry. But ultimately, I want to only be able to talk about these objects. I don't want to refer to the spacetime. I want the spacetime to emerge from all that structure that's hidden there. I will come to it in a minute. Yeah. So how do I so ordering and causal order is easy, because if I embed something into a set of points, then I can induce a causal ordering on them and construct a post set. But I also want to make sure that there is a number to spacetime volume correspondence, and that's not easy. So if I take a regular lattice, like I take a light cone lattice in 2D, that's not going to satisfy this in all frames. And I need it to be satisfied in a covariant manner. Otherwise, I won't be able to recover spacetime, because spacetime is covariantly defined. That geometry, I won't be able to recover. So the way to do it is via a Poisson point process. And here's an example of that. You'll keep seeing this picture through the talk. A point process in 2 dimensions. And you induce the causal relations from there. And on an average, there's a number to volume correspondence. And the Poisson point process tells you that in any region of volume V in the spacetime, the probability that you'll get n elements in that is given by this. So interestingly and importantly, this random lattice preserves Lorentz invariance when the underlying spacetime is Minkowski. And there's also an interesting non-locality, which basically corresponds to the fact that the resulting graph does not have a finite or fixed valency. This makes it very different from causal dynamical triangulations. Sometimes people get confused with the term causal in both. So both require causal ordering, but because of this number to spacetime volume correspondence, which is done via this Poisson point process, you have a non-locality, which is basically due to the fact that, I mean, this is the nature of Minkowski spacetime. If you look at the constant, the invariant hyperbole, say in Minkowski spacetime, of invariant hyperbole corresponding to a fixed proper time from a particle, that is a non-compact surface, right? I mean, these invariant hyperbole are non-compact surfaces, and it essentially means that for every point here, the set of nearest neighbors, say in Minkowski spacetime, is infinite, either both to the past and to the future. For a finite one, what you have is a graph which is not a fixed valency. So a continuum like causal set is like a random lattice. But of course, causal sets more generally may not have continuum approximations, and typically do not. And again, for those of you who remember Faye's talk from last week, that was part of the discussion that was going on. Now, one of the important class of questions we worry about is how much information can you get out of it? Because we've made this claim that we have a fundamental cutoff. So how much of space-time can you recover from this discrete construction that we've done? And that's important because, in fact, if you have to recover space-time, then there should be enough information in here, right? I mean, I have to go there and pick out the information from here. And really what I'm doing is I've got, for every space-time, an ensemble of causal sets because it's a Poisson point process. So I have an entire random variable associated with it, and I need that random variable to have enough information to extract geometric data. And here's sort of our library or our list of things that we can get out from causal sets. The simplest is time-like distance. Yeah, I think I mixed up the two here. Sorry. This reference is Brightwell and Gregory is at time-like distance, where you basically look at a Lorentzian distance, which is the length of the longest chain that you can construct between the 2 points. So Lorentzian distance is always maximized distance. So the same kind of thing, you look for the length of the longest chain. And you can show that in the rho going to, or the discreteness scale going to zero limit, or the density going to infinity limit, that these things recover all your continuum properties. There's one in particular, and so I've just listed them here. I don't have time to go over it, but if you have any questions, we can talk about it later. Of particular relevance, of course, is the Einstein-Hilbert action, because once you have it, you can start to construct a dynamics for your theory in the way that the Reggie action is used in CDTs, right? So you need an action on the discrete substructure, which is intrinsic to this discrete substructure, and then you can actually construct a dynamics. Importantly, what all of this is, these are constructed out of what are called order invariants. So they don't care how the elements are labeled. Okay, so it's a label invariant thing that you're taking out. For example, if you were to calculate the number of nearest neighbors in this, or the number of relations in this, it doesn't care how you label the elements. That's an order invariant. So what we find is that covariant observables correspond to order invariants. So here's a discrete Einstein-Hilbert action, or the Benincasa-Dauka-Glaser class of actions. And this is a very beautiful construction. It has a very nice answer, which is that you can basically construct your action out of counting causal diamonds. And let me try to explain that. I think Faye explained it last week. I'll remind you again about it. If I have two elements which are nearest neighbors, then that counts for this number n0. So this is the four-dimensional action. This is the action more generally where, so let me just look at the four-dimensional action. This n0 corresponds to the number of nearest neighbors. And then I count the number of next to nearest neighbors. In other words, these are deemed to be next to nearest if there's only one single element that lies between them or in their Alexandrov interval. And then this next term, n2, corresponds to both these situations where you can have two elements between them and so on. So you're basically summing in a finite element causal set in a finite volume of spacetime. If you want to give the action, tell me what the action is, the Einstein-Hilbert action. I just have to count these various intervals in the causal set, put them in this particular curious combination with alternating signs, which is very important. And that will give me, in the limit, the Einstein-Hilbert action with boundary terms. Okay. We know something about these boundary terms, but I won't talk about that at all today. What do these nearest neighbors look like? If you think of a single element here, and I look at its past, then its past is foliated by these, these hypersurfaces, these space-like hypersurfaces, which distinguish between the nearest neighbor, next to nearest neighbor, and so on. And it's a foliation, it's an infinite foliation. These are non-compact surfaces, and that reflects the Lorentzian character of the space. So, okay, so now let me ask the question. Now that I have this action, I can ask, well, let me try to do the naivest thing possible, which is let me try to construct a quantum theory out of it, write down my quantum partition function. Okay, but now I'm going to sum over causal sets. I'm not summing over manifolds. My fundamental deep structure is not a metric theory. It's a theory of locally finite partially ordered sets. And I'm going to do one thing, which is I'm going to restrict the number of elements, and then I will look at the asymptotically, I'll look at n going to infinity in some cases, or I might not want to do that. So fixing n, I have a finite space omega n. And so the sum is over a finite number of elements, but as n becomes larger and larger, of course, this set grows, and I will explain to you shortly how that set grows. So here's a representative of a sample space of all n-element causal sets. So there's three approaches, so to speak, that we have to dynamics. Why do we have three approaches? Because we don't know how much of the big elephant of quantum gravity we can reach. So this is the Lorentzian path sum, which is, where you have full quantum path sum, a sum because we're just literally summing over a finite number of causal sets. And then you can do an analytic continuation of it without losing the causality that's inbuilt into this space. And I will describe these two. I'll actually start with the second one and then go on to the first. And then there's another more fundamental dynamics, because you can always ask the question, well, if this is really the fundamental structure, why do you want to start with something like the continuum to derive your Einstein-Hilbert action? Is there not something more fundamental? And so this is the sequential growth dynamics, and the best way to describe it is in terms of a decoherence functional. I'm not going to talk about this at all because that's an entirely big talk in terms of the technology that you have to use to even begin to discuss it. And we're not very advanced in our understanding of these models. We have some understanding, and we have existence theorems, but nothing like space-time. So, okay, so let's go to the Lorentzian state sum. Here, what we do is we introduce a parameter, an analytic continuation parameter, and we use that to define a state, what one might call a state sum model or a statistical theory of Lorentzian geometry. Okay. And this beta is your analytic continuation parameter. And the idea is to use those order invariants and evaluate their expectation values using Markov chain Monte Carlo techniques and see how they change with with beta. Okay, so as beta varies, see how they change. And the kind of order invariants we would look at are dimension estimators, which f of d here is a given ratio of gamma functions. And whether, what your dimension estimator gives you something that's an integer or a non-integer value to give you the dimension of the spacetime. And the proper time, like I said, is the length of the longest chain. So you can look at the height of the poset. All of these are good variables. And also looking at the number of intervals you have in the causal set of different sizes. So this is actually a very constraining observable as well. And the action is another, and so on. So let me just very briefly tell you about work that we have done. I will just give you results of the numerical simulations, but at any point, if you had questions about it, I can talk to you about it. So one of the things is that we tried to start with the full space of causal sets, but it's a very difficult thing to work with. We actually did do some work on it a while ago, just to understand the nature of the space without putting on an action. And we could see that certain asymptotic behavior we could find. But the moves are very hard to model. So it's one of the things to do is to basically say, let's not look at the big pie. Let's take a little bite. And the little bite is to make a dimensional restriction. It's still non-perturbative. But because causal sets don't have dimensions inbuilt into it, you can say, well, let me do something reasonable. Let me inbuild dimension and then look at only that class. And so that's what we did. So we studied things that basically look like, that can sort of approximate 2D intervals, a 2D cylinder, as well as a 3D case, which is a two torus cross the interval. So let me just go over the 2D orders case, because this is the one that's most studied. And it's very fun and easy to understand. So if I take a diamond like this in two-dimensional space-time, and I have the u coordinates and the v coordinates, or u coordinates and v coordinates, then I lattice it. And that latticization provides me with a set u1 to un, which takes values in 1 to n. And I will say that this set here is ordered, fully ordered, and this set here is fully ordered. But I can construct a partial order by taking the intersection of these two sets in the following way. I will say that an element EI in this intersection precedes EJ if both the UI values, if the UI value is less than that of UJ and VI is less than VJ. So that's the condition for a relation. And so that constructs for me a very nice mathematical object, which is called a two-dimensional order. I mean, these are studied by mathematicians. They're order theoretically interesting objects. And now I can do a move, Monte Carlo move, Markov chain Monte Carlo move, which is very easy. I can flip them around. And by flipping it around, I basically walk through my space of 2D orders, and I can generate, study the observables and so on. In the higher dimensional cases, actually even in the cylinder, you can't use this simple structure. But what we did was we used, again, a latticization, but a more convenient one, where you have m sites and n occupancies, and you construct an occupation matrix. And the Monte Carlo move is just simply to move this around. And the order is deduced from the embedding into the lattice here. So what we found was very interesting and seems to be somewhat universal. And that is that there is a first order phase transition in this theory when so here's an example of what happens to the action. This was many years ago, the data from then, but we've reproduced it in multiple ways later. So if you take the action and you vary with beta, you find this transition here. We studied this very carefully and looked at finite size scaling effects to see whether there was a change, and we found very nice collapse structure. And so we're fairly convinced. We did a lot of tests to check for whether it's a first order phase transition or not. And we find that that's, in the 2D case at least, we're absolutely sure. In the higher dimensional, the S1 cross I case, the cylinder case, as well as the torus case, again, we see a very similar transition. What are the two phases? What's interesting about these two phases is the following. The first phase, that is for low beta, which is for high temperature, it's the random phase, which looks like spacetime. Okay, so the dynamics spits out this, okay, I don't know how that happened. The dynamic spits out continuum spacetime in one phase. The other phase is highly ordered. It has this very layered structure to it. And if I were to, so you can say, well, this is, what is it actually telling you physically? This is just the, just the observables in these two phases. And I'm going to refer to old work that we did in the 2D case, where we constructed a Hartle-Hawking wave function, which is sort of the analog, the discrete analog of what you would do in the continuum, which would be to sum over all spaces with a final boundary, right? So the Hartle-Hawking wave function, so maybe this I can I would basically write it just roughly as something with a boundary geometry, and I would write it as a sum over all manifolds, and I would write it as an e to the minus beta of s of m, where dm, so I'm summing over all m such that this is equal to this, and I have a where g, boundary of g is equal to h. Okay, so that's my analog, and I'm doing a discretization of this, and this gives me a way to calculate the Hartle-Hawking wave function. And in that case, there are these two phases appear in a different way. What's interesting, so you have one continuum phase, and what's really nice is that there's actually peaks about certain geometries. So even when you vary over n and you change beta, so these are different values of beta, the different colors, but in the low temperature regime, you get a very distinct peak over geometries of this kind. And at high temperatures, you get a peak on geometries of this kind. Sorry, low temperatures this kind and high temperatures this. So I got that. Yeah, it's inverse beta, sorry. So what is interesting about this phase is it's a very connected phase. You starts off with a single element and suddenly explodes into a very large spatial size. And a second spatial slice comes into existence, and everything is connected with everything else. So this is not something that embeds into space-time. This is not a continuum-like object, but it has all the nice properties that you might want in an early universe. And so I just want to put it out there. We don't really know. This isn't well worked out in terms of, but it's a question that does arise. Is this a mechanism for scale invariance in the early universe, for having no horizons, and so on? And I think even taking this model into the higher dimensional case is something that we should be doing. We haven't done so far. Okay, so I'm going to, yeah. We did it in, it's the statistical part sum. So we use the statistical measure, but the summation is over Lorentzian objects. So it's Lorentzian in that sense, but it's statistical. It's not quantum, it's statistical. So insofar as it's a continuation of something in the quantum case. We don't know yet. We don't have theorems to tell us. But yeah, so this is but in term, as the Hartle-Hawking wave function, because it is defined in the Euclidean path integral, but the pieces we're putting in are Lorentzian. But the action itself, this term here, is basically allows you to think think of it in a statistical way. So, in some sense, this is the best interpretation we have of that theory. So let me come to the Lorentzian part sum, where we're no longer doing any. We're not doing any analytic continuation. We still have an oscillatory path integral, or now state path sum. And again, those of you who might remember from last week, the question we now have to ask, and this is an unrestricted sum. This is the sum over all possible n-element causal sets. And that sum contains these beasts, or bad guys, or however you want to call them. First of all, you notice this was enumerated by Kleitman and Rothschild in the 70s. What is as n increases, what is the size of the space? How many causal sets do you generate? And you have the super exponential growth. And that super exponential growth is completely dominated by objects of this kind. So in other words, almost surely a causal set, if you just pick from the bag of causal sets, is a Kleitman-Rothschild poset. The characteristic that it has, which I've written down here, is that approximately the bottom layer has 1/4 of the number, the middle layer has a half, and the top has 1/4. And there's a specific connectivity that every element here is connected to approximately half the elements in the middle layer, and every element on top is connected to half the elements in the middle layer, and every element at the bottom is connected to every element on the top. This is the structure of this guy. And like I said, we did look at the onset of this. We did examine such things in the full sample space using Monte Carlo methods as well. And we know that this asymptotic regime appears around n equals 100. So by the time you get to n equal to 100 Planck volumes, you're in a mess, because these are the dominant objects that you have. So why are they bad? Because if I take all my slew of, continuum-like order invariants, and I put them and I check what their values are, I know that this object is not like a continuum. I mean, it's kind of obvious when you look at it, but it may not. I mean, just to be absolutely sure, you want to check with these various variables. And you find, for example, that for a Kleitman-Rothschild poset, the dimension is 2.5. It's not an integer dimension. And this is in the large n limit. And if you look at the intervals and the size of intervals and the abundance, how many they are in the causal set, then it has this very peculiar feature. It sort of is very sparse for low values of the interval, except for the links, which are the nearest neighbors, which is very high. And then it suddenly has a bump later on. So this is very different from the continuum, where there's a very nice, actually a nice hypergeometric function, which gives you this. So we want to make sure that these things don't show up. Otherwise, our path integral is dead. It's just totally swamped by these objects. And if we got rid of the 3-layer ones, then Dhar and others have shown that basically there's a subdominant contribution, which is also of order 2 to the n squared, but now the factor is not 1/4, it's smaller than 1/4, and so on. So you get this entire hierarchy. And the question you want to ask is does this meager little thing, the Einstein-Hilbert action, is it enough to defeat that entropic contribution? And that's the worry that we would have, because if it can't, then we are basically going to have to change the nature of the question, right? I mean, otherwise we're totally going to get things that look nothing like the continuum. And so it's been a long-standing question. In the remaining 5 minutes, I'm going to try to run through the ideas here, which is that it started off with a very nice calculation due to Carlip and his student Sam Loomis, where they just looked at the case of the bilayer poset, which is a subdominant contribution. It also grows like 2 to the n squared upon 4. The number grows as you get to larger and larger n. But now it's a very simple structure. There's just 2 layers. So if I look at the action, then I don't need to, I have nothing else. All the intervals are just nearest neighbors, right? I mean, I have no next to nearest neighbors possible because I have things are just arranged in 2 different layers. So I have a much simplified action to calculate. And what you can show, and they had a very nice counting argument, which allows you to rewrite this integral, this path sum as an integral, but now over the fraction of links that you have in any given causal set. And this measure is not trivial to calculate, but one can use combinatorics and calculate it. And basically you get a contribution just from these bilayers, which looks like this, where this object here is what is Dhar's entropy function. And if you go about this calculation and do a saddle point approximation and also worry about, all fluctuations, which is what they did in that paper, then you find something very interesting. You find that when the discreteness scale, and so this is something I should have reminded you, sorry. Yeah, there's a discreteness scale that comes in here, which is L, and this is the Planck scale. When the discreteness scale is greater than some value L naught, then this thing leads to a suppression, and that L naught is bounded in this way. In other words, that L naught for 4 dimensions is 1.136 times the Planck length, and it's really bounded for all dimensions in a very small, tight range. So we started off with nothing. We started off with just the partition function over these bilayer posets, stuck in the Einstein-Hilbert action, which simplifies in this case to the link action, and out comes a constraint on the Planck, on the discreteness scale, which is pretty much the same as a Planck scale. I find this really fascinating. We then extended this using, again, the link action because we thought it was too complicated to look at the full action. Let's just try to see what happens with the link action. And we found the same suppression, even for all the higher order ones, including the ones that are most dominant. And then, of course, the question was, is our assumption of using just the links enough? And that's what we've been doing for a while, which is a lot of messy combinatorics, trying to understand whether the link action suffices. And indeed it does. So basically, we have this, putting all of this together, we have, and I mean, I can go through this at any point, but we we find that there is a complete suppression for the same set of range of values. And so what we see is that just that simple requirement that this is your, we started off with this partition function here, and we asked for the contributions from these most dominant entropic causal sets, and we find that they're actually suppressed by the Einstein-Hilbert action. And this is a exact calculation. I mean, it's a saddle point calculation, but because of the n squared, everything else is completely swamped out, okay? So let me ask the question then, which is something that is ongoing work. I had hoped to make more progress on this, but it requires a certain amount of numerics that I was too lazy to do. Which is the question, but okay, it's all very well for entropic contributions to go away, but what about the continuum-like contributions? And here there's sort of an argument. You can say that, well, let me look at just the contribution from a manifold-like causal set. That corresponds to an entire range of causal sets, which which are from the Poisson point process. Okay, so there's a whole set of non-zero measure in the space of causal sets, which I have to do the summation over. But here I can write the action as coming from the mean, which I know to be a constant for a manifold-like causal set, from the limit of in the limit of large n, plus a fluctuation. And then my integral actually surprisingly just reduces to something quite simple, which I can evaluate. And here's an if, because this is something that requires numerical evidence, which I don't have as yet. Then I would say that a manifold-like causal set would basically, up to normalization, not be suppressed in this path integral because of the causal set action. On the other hand, if the dimension is not the same of the manifold that is contributing, is not the same as the dimension of the action, then this contribution of these objects here goes like this. It goes like an n squared, and that then basically gives rise to a very oscillatory integral, and in the large n, that oscillatory integral contribution should presumably not matter at all. So this is speculative, but I think maybe we can conclude saying that spacetime like causal sets of dimension 4 may just have a fighting chance. So dimension, whatever you like, 126, 26, whichever one you want. But right now we don't have a way of saying that from a more fundamental perspective, because the action has a dimension that goes in. There are some new developments which I just wanted to highlight, the things that I think are very interesting, especially from the perspective of this conference. There's work of Icon and her collaborators where they look at higher order curvature operators in causal set quantum gravity. And I think Astrid has a very interesting perspective on causal sets, which is that they're useful ways of regulating your theory as a regulator of the continuum. It's covariant. So even if you don't believe in causal set theory, it's a useful thing to do because you have a covariant way to implement cutoffs. And you could do quantum field theory. We do quantum field theory on these things. And, maybe that has a certain, you can take limits then in a much more careful way. And so this is a sort of program, I would say, she's been talking about and initiated. And the idea is eventually, when you have these higher order curvature operators, so she has some very nice terms that emerge, can we use these tools of EFT to study causal set theory? And then a question to the asymptotic safety community is, does a discrete theory have to be asymptotically safe? And then also some unrelated, but also related to the kinds of questions that people have been asking here, work of Faye and her students, which is students and postdoc, which is how to deal with interacting scalar field theories on causal sets. So as I said, you can think of causal sets as a regulator for quantum field theory. You can write down the free quantum field theory on causal sets. For a scalar field, we are limited in the kind of matter we can put on causal sets. But for that, we have a very nice covariant way to define the vacuum on this, which is called the Sorkin-Johnston vacuum. And they have recently come up with an interacting scalar field to put in interactions, like 5-4 interactions. I should also put in Kasia Reisner and Chris Fuster, maybe one more collaborator into this list I forgot, because they also suggested similar techniques. And here it's based on an in formalism, partly because you have access to the same quote-unquote Hilbert space or the same state. And they're, exploring these questions. And I think this is something to look out for in causal set theory. So here's in conclusion, it's a non-metric poset-based theory of quantum gravity. There's a well-defined continuum approximation with an inbuilt UV regulator. We have looked at quantum dynamics, and there are interesting questions that remain to be answered. And I'll just leave it at that. Thank you.
And questions, please.
You mentioned adding matter. Can you tell me how you represent the fundamental degrees of freedom of the theory, and is there a canonical version of this theory?
Right. So is there a canonical version in the sense of a Hamiltonian?
Physics predicting the future from some knowledge of unique knowledge of on a Cauchy surface. I can't see anything like that in your
Right. There are, so that's right. So we don't, so what is natural I mean, that's why we use a path integral. We use a sum over histories approach. And the reason is that if I try to, I mean, we can get some information about spatial hypersurfaces, okay, some geometric information. Those are things we've tried to do, and we've been partially successful. But here's the problem with it, and that is that if I have a random structure of this sort, then space-like hypersurface are a set of points which are unrelated to each other. Okay, so that's fine. But I want this to be, so I'm going to call this an anti-chain, not a chain, an anti-chain. And that's fine. That tells you that it's a space-like hypersurface. And you can make it maximal so that there's no other elements that are, everything is either to its future or to its past. So there's a nice causal way of describing that. However, if you want it to be Cauchy, right, you have to make sure that this captures all the information, is a summary of its past, so to speak, right? I mean, how do you summarize a past in this case? I mean, you would if every element in the past had.
That's why your comment about the matter contribution fascinated me, because you mentioned it was being done in the in formalism.
Right.
That would necessarily imply that you could talk about evolution of a
Right.
state. You had a notion of a state on a constant surface, and you could talk about its evolution.
So actually, they do it in the Heisenberg picture where the operators are revolving, not the state. So that's fine. So, but the point is that that's actually very important, technically very important, because the in state. So you can always define a boundary, like an initial boundary and a final boundary in the causal set. That's perfectly fine. But when the reason that this transition is not so easy within the causal set to make clear, although I think the plan is to
have something, but
yes,
doing it in the
so the in formalism is to come back basically to look at this state, and you're looking at the double path integral. So you're looking at all the configurations that are forward in time and backward in time. So
okay, fine, but they're talking about evolution of an expectation values of operators. They must have a way of answering this question about what's the canonical structure. First, what's the irreducible state of what's a complete and completely reduced description of all physics at a particular instant. Usually it would be the P's and Q's on some Cauchy surface.
Right. So let me just say why there are no Cauchy surfaces. There are boundaries which are space-like, and there are, either to the past or to the future, but they can't be Cauchy hypersurfaces for the following reason in what we do. You may not like it, which is fine, but that's the nature of this discretization. So you would imagine that if you have to be a summary of the past, that all the information, that every element here is to the past of some element here. Okay, so so let me sort of label the anti-chain elements here. So anything to the past anything here is to the past or to the future. But I can still have relations, fundamental relations, which are not obtained through transitivity between an element here and an element there. So when you try to construct these space-like hypersurfaces, right, in the causal set, they're more like Cauchy sieves They're all possible links of this sort, and that has to do with the non-locality of the theory. Having said that, if you have a propagation of a field, and you were able to not talk about a single, you weren't talking about a single anti-chain, but a sort of thickened, more continuum-like region of the region of the causal set, then this not unlike what you do even in AQFT, where you never do supports on.
I understand the complication that you're talking
Okay.
about. About pure gravity, but the people who you told us
Okay.
do an informalism, they must mean something. And they must have somehow got an answer to this. What's their answer to it?
If I may suggest, can we continue this question in the discussion session?
Sure.
Yeah.
Okay.
Are
I
there any
may
other
still not be
questions?
able to answer it, but yeah. I mean, it's one of those things that are, yeah.
Thanks very much for your nice talk. I have a very naive question. In your one of slides, you talk about this beta C. Is beta C is model dependent or is dimension dependent? It's always derived from some first principle. I mean, just wondering.
Right.
How do you find these things?
So that's a very good question. You're asking, I think, about when this phase transition happens. Right. So when does this phase transition happen? And for a given, so let's just look at one particular model where, the two-dimensional case. And you can ask us, the reason we did finite size scaling is because we wanted to see how do we scale the rest of the parameters of the theory in order to have collapse at the same point. So in a sense, not the raw beta C here, but there's a scaled version of beta C which represents this particular phase transition. And that's what is here. The particular value at which this happens, I don't think we have a very good understanding of how that. We have a way of seeing how it relates to n, but not to dimension, not to space-time dimension necessarily. But it's, in a sense, you can imagine it as the attempt. So if I look at the number of links, so the action had links plus the next to nearest neighbors and so on. The links can completely dominate in certain configurations, as we saw even for those the layered posets. And when that happens, that particular set of configurations completely overwhelms anything else. So it's the sort of interplay between that and the sort of, in this case, the entropic contribution from these kinds of configurations. So at some point, and this is a fairly sharp transition that you see. I mean, this is just for n equal to small n values, but as you get to larger and larger, the transition gets quite sharp. It's and that's where the dimension may matter, because the dimension tells you what kind of an action you have, and the topology will also tell you what kind of terms will contribute more. And so there is some interplay, but I don't think we have any idea whether it's universal. We haven't studied it enough to be able to extract anything universal. But thanks for the question.
Your graph show the two-dimensional. This is a two-dimensional result.
This is two-dimensional, and we have similar things for this S1 cross I as well as a T2 cross I. So we have similar phase transitions. I just didn't show all of the graphs here. But we've
at the same scale.
Sorry?
Is the different topology show roughly the same scale when this transition happens, or is not?
Are you saying that the different topologies show up? You mean to say again with beta C? Yes. I don't know. I mean, we haven't studied these systems well enough to be able to compare across models to see where the role of topology comes in. It's a very good question. I think if one maybe looked at the actions a bit more carefully to see what is the scale at which this happens. All of this is numerical because it's very hard to do it analytically. But even the numerics, maybe it warrants some more comparison, which we haven't done across these different cases. So, thanks.
Okay, I think it's time for coffee. So we will combine after the coffee break. Let's thank Sumati again.